Thank you, Hugh. Thank you to the organizing committee for putting this together and housing the speakers. It's a topic I'm very interested in. I have a slightly different angle on it, retro-causality and freedom of the will, as you'll see. But it all stems from thinking about the statistical independence condition in Bell's theorem. So we're off to a great start here. I told you, Hugh, this worked an hour ago, so it definitely won't work now. Good. So Bell's theorem has been widely understood. This is pretty much review, but just let me frame what I'm going to say. To show that any theory that reproduces the quantum predictions for EPR type experiments must violate either outcome independence or parameter independence. And the conjunction of these two is sometimes referred to as strong locality or just locality. So many years, so many words. We've generated more words this meeting. And I hope that will continue for the next 50 years of discussions about Bell's theorem. In any case, I'm going to probably try to minimize my production of new language, but there may be a little bit. What I want to focus on, though, this analysis is goes along with the general claim that quantum mechanics, any theory that's going to reproduce quantum mechanics is going to be non-local. I think that statistical independence, the violation of it, is, I keep hitting the wrong button. What does the bottom button do? Oh, it's the mute. Here we go. Statistical independence has associated with retrocausality. And I think, for me, the concept of retrocausality is problematic, but I like the idea of trying to understand what violation of statistical independence would mean. I think it would be a whole talk to talk about why I find it problematic. I don't know that I have a completely decisive argument, but it's not really important. What I want to do is give a different way, and I think possibly more intuitive way of thinking about statistical independence, which might lead to thinking of a different class of models. So what I'm not doing, by the way, at this conference, I've noticed is sort of a mixture of reformulations of quantum mechanics and attempts to provide new models which underlie quantum mechanics, sometimes an awkward mixture. But this is going to be in the category of the latter, okay? Just gesturing toward providing a new model for quantum type phenomena. I'm not using the quantum state, forward, backward, split, absorbed, unabsorbed, any of that. So this is just the statistical independence condition. The probability of lambda given A and B is equal to the probability of lambda where A and B are the settings of two detectors A and B in an EPR experiment. And lambda is the state, whatever that means exactly, of the system under investigation. So in quantum mechanical models, it's typically a singlet state of a pair of particles, an entangled state. So more generally, I take it that the idea, the intuitive idea behind this and the reason that people hew to it is that the idea that the state of the system to be measured is independent of the state of the measuring device. Okay? So this is a space-time schematic for EPR. This is just really, I think, motivates the reason for thinking that there might be a connection between measurement settings and the state lambda, which I have localized here as if it were the particles were located at a particular place. The idea is simply that that lambda is causally connected with the detector, or causally connectable, as it must be if it's ever to be detected. And the backwards causation idea is roughly that the setting up here can somehow influence this is one version of backwards causation, can influence the original state. So that this original state already has knowledge in some sense of the final detector settings. Okay. Now, I think that I'm not averse to talking about correlations, and you'll see how I think about them in a second. I'm a little reluctant to describe them as causal. So, that's neither here nor there. This is the beginnings of how I like to think about it. This is the path domain of dependence of the detector, okay, of detector A. And this is the path domain of dependence of detector B. And we can assume, I think, that mu A, the data in this is a, well, what would it be? It would be a circle in 2 dimensions. Anyway, the data on this ellipse minus lambda. So mu A plus lambda determines, is fully determinate for the detector setting. What I'm doing here, I am assuming a kind of relativistic determinism. I'm assuming that influences travel in light cones. If I don't do that, we could do this conceivably with the stochastic theory. In that a stochastic theory would be one in which this data generated outcomes here, detector settings with various probabilities. But I think that if one doesn't do that, then one has to question why one is using a Minkowski space-time at all to frame the problem. Okay. Essentially, I'm assuming that the matter, the influences in here are such that what happens here can be predicted on the basis of what happens here. All right, so that's the causal path to the detectors. This detector then is, the thinking behind this is, okay, certainly you could just leave the detector, you could set it here, it could be set already, and it could remain in its present setting. Or you could have, as in the actual experiments, or some of them, of aspect, and maybe others, I don't remember who's done what. You can introduce a kind of a randomized oscillation to jiggle this setting. So that's allowed, but everything that influences this setting is going to be in this light cone. So all the information to predict what the detector setting in here is going to be a product of lambda and mu B, and over here mu A and lambda. Okay, so what I want to talk about then is, let me just say, I want to kind of motivate this particular way of thinking about it that is at the bottom of the slide, and then I'm going to give you 2 examples closely related. So it should be, hopefully we'll keep this short. I want to think about statistical independence in terms of the initial data. So this is what I've written down here is the condition, the conditional probability, the probability of lambda given A and B, should be equal to the probability of lambda given mu A, mu B, and lambda. These are the things that determine A and B. Okay, and clearly we can remove the lambda since the probability of lambda given lambda is 1, I believe. So the probability of lambda A and B is going to be equal to the probability of lambda given mu A given and mu B. And if we have if this expression, if that conditional probability does not equal the probability of lambda, we have a non-local constraint. So the argument is this is a form of statistical independence, but it is statistical independence written in terms of not of the final detector settings, but of the initial data which generates the final detector settings. Sure. Yeah.
So a short technical question.
Yeah, good.
The domains of dependence, mu.
I'm sorry?
Do they include lambda or not?
Mu?
Yeah.
No, I meant to. I had to redo all these slides today, so it's a little unclear. Lambda and mu are mutually exclusive. So the total, one of those ellipses is a little corner of lambda, and the rest is mu.
Is that last one short for lambda given UA prime and UB prime, or some other?
What are mu?
Probably lambda given. Given no information. What that very last term?
This?
Yeah.
Well, I intended it to be the same thing it means in the ordinary statement of statistical independence, which is that the probability distribution of the hidden variables, lambda, is independent of the data elsewhere on the initial data surface, or equivalently independent of the future detector settings. Does that make sense?
Yeah.
Yeah. I don't know what the...
I know what you mean.
You know what I mean? All right. Does anybody else know what I mean, or is Ken the only one? I'm hoping more than one. Okay. So this implies... Oh, God. Here we go. I have to go back. This is a non-local constraint. So what it's saying is that the probability of a given lambda is going to depend on the data elsewhere on that initial surface. That's what I intend this to mean. Well, I think it does mean, but and I'm calling that a non-local constraint. It's a non-local constraint because the data is space-like separated. Just by way of comparison, obviously what I put up here, you've already seen it. It's a local constraint, like Gauss's laws. For electromagnetism with sources, divergence of the electric field is equal to 4 pi in appropriate units, 4 pi rho, the charge density. In vacuum, it's equal to 0, and always the divergence of the magnetic field is 0. So what does that mean? That means you can't specify the magnetic field arbitrarily everywhere on your initial surface. This is straight Maxwell theory. That's a local constraint because it applies point by point. And here it's quite evident if you think it's the same really all around. But what's the constraint on the electric field at a point? Well, it has to do with the charge density at that point. Okay, so that's a local constraint in contrast to the kind of constraint that I'm introducing here. You can get a non-local constraint from topology. This is another way to think about how a non-local constraint can originate. It's not the way I'm going to develop. This is an overly simple diagram. This is supposed to be, here we are, x, t. So this is a flat space-time wrapped up on a cylinder. So it has closed time-like curves. And the idea here is that if you, in an ordinary space-time, you could put particles anywhere along this, say, initial data surface, if I may call it that, and give them any particular velocity. Okay? Can't do that here. We have a consistency constraint, which is a non-local constraint. So if I start a particle here with this velocity, then that's what I have to have, at least that. Okay, the particle's going to wrap around. This is assuming, obviously, it's a free particle. It's not interacting with anything. If there are any interactions in here, well, God help you. This is wrapping around, and what it means is it's inconsistent to postulate the existence of a single particle at one point. Rather, there have to be a multiplicity of them. The only way you can have a single particle is if it wraps directly around. It has zero initial velocity with respect to this privileged slicing, and then you would have a single loop that repeats itself. Okay, so that's a kind of non-local constraint. Just to, in contrast to the Gauss law. And nonlinear constraints in iTunes, some of my favorite examples. I've been doing a lot of recording lately and thinking about digital audio and how it works. And it's actually quite interesting and happens to yield a good example for my purposes. So, the main principle behind digital audio, as many of you know, is that any analog function whose Fourier transform is band limited can be digitally encoded with perfect accuracy. Now, the perfect accuracy depends on sampling the function infinitely far out and with arbitrarily high accuracy at each point. I'll show you what that means. But in general, this works quite well, even in the kind of land of effective digital audio, which is CD player or the files on your computer. So audio signals containing frequencies no higher than 20 kilohertz can be perfectly reproduced from samples taken at a frequency of 40 kilohertz. So this is going to be an example in time, not in space. I'm going to be talking about a signal dispersed in time and frequency rather than space and wave number, but the principle is the same. Okay, this is called the Nyquist rate, and it was or sometimes the Nyquist-Shannon rate. It comes from the early to middle part of the 20th century, this realization. But it's a fairly straightforward consequence of Fourier analysis. So the way music is actually encoded when it's done properly is that signals above 20,000 hertz in the recording process are filtered out. And filtering them properly is requires a little bit of clever engineering, although some allowance is made for lack of perfection because the CDs actually sample at 44.1 kilohertz. So the ceiling is a little higher. But that's what happens. The idea is that, okay, here's your audio signal, and I'll show you a real audio signal in a second. It's a signal that goes on in time. It has amplitudes at various times. When you're doing this, you always have a maximum amplitude, so the signal is normalized. And these are 1/40,000th of a second apart, and you record the height of that, the amplitude of that signal every 1/40,000th of a second. And remarkably enough, you can completely reproduce this curve. Okay? You don't have any ambiguity as to how to interpolate. That's what's kind of interesting. It's not just a matter of drawing a straight line between samples and hoping nobody notices. Okay? So, nor is it a matter of just sticking in little step functions here. Okay, so that's how digital audio works. But let me see what I have next. So this is an example. This is my duet partner on a song I just recorded. This is her entry into the song. I don't know. This is probably breathing over here, and probably really sophisticated audiophiles here can see exactly what she's singing and what the notes are. That'll be write it down, and there'll be a prize of a pint of your favorite bitter for the winner. Okay, that's what it looks like. This is over the course of what is it? This is 4 seconds, and that's coming in. This is the beginning of the chorus, and so we're sort of zooming in on one point. This is what it looks like. Roughly coming in further. And right now, what we have here is these are actually, this is the sample interval, if I'm not mistaken. This is the grid. So this is, what you're seeing here is a smooth curve that the computer has reconstructed from discrete samples at each one of those lines. And how is this non-local? It's non-local in many respects. I mean, but here's a very obvious way. If I know the function here and here, I've fully determined it here. Okay? This is a result of the fact that this function is band limited, so that there are no sine or cosine waves higher than 20,000 hertz that are used to construct this signal. So that's a kind of non-locality, and you can think of this perhaps as this is our little lambda. This might be the mu A. This is mu B. So this is a situation in which mu A, specifying mu A and mu B fully determines lambda. Okay. Now, that's kind of a nice example, I think, of a non-local constraint. But I also think that if you're going to have any chance of reproducing quantum mechanics, you really need to figure out where the action comes in, where Planck's constant comes in. Planck's constant, though people set it to 1 and forget about it a lot of the time, is actually a dimensionful number. It has units of action or angular momentum. I mean, we all know this, but it often kind of goes missing in toy examples. And it's certainly essential, it has to be essential to getting back the right classical limit. The size of Planck's constant is going to be important. So what I did is, this is not going to generate quantum mechanics all by itself. But if you have a simple model like this, what you're doing, what's the interesting parameter? The interesting parameter is the cutoff frequency. You're band limiting it. What's the limit? Where's the cutoff come from? Well, you can take the Compton wavelength of the particles of interest. That would be one thing you could do. And if you do that, you get a number. So you get K is the wave number. That's the frequency in space. And rest mass times C divided by H. All right, and it's H that lets you basically convert, as you know, a momentum into something that has to do with space. All right. It's the existence of H that tells us that position and momentum and energy and time are the things that don't commute. And it's that gives us many of the remarkable results of quantum mechanics, which is why we use it in the first place. We don't use it for EPR experiments generally. We use it to understand the stability of matter, and which is what it was originally, one of the two things it was originally invented for. So I think it's important. So the point here is you come up with a model, non-local constraint. Here's a non-local constraint. You want to figure out, if you want to apply it to quantum mechanics, how, where H is going to come in. What is going to be non-local and how is it going to be non-localized or delocalized? Okay, let me say a little bit about free will. We just started talking about it in Ruth's talk. It's been conspicuously avoided for much of the conference, but Adrian?
Yeah, I was just wondering if you could join the dots. The idea is that
join the knots?
Dots between...
Oh, the dots, okay.
Discussion of
right.
variables and the discussion of bandwidths.
Yeah.
Is the idea that we have some sort of field, hidden variable field corresponding to each particle, and you've got some... I don't, I thought about that. I don't particularly like that. I think that's too problematic. I mean, if you have more than one particle, you're not going to have a field on a line. Even if the particles are confined to a line, the configuration space is two. It's really sort of it's a model that's, I wouldn't build this in its current state into a model for quantum mechanics. It's really more a model of a theory in which initial data is non-locally constrained, and which naturally would violate statistical independence. It's not. So one of the points here is it's not a particularly exotic theory. In fact, this is just standard engineering, and you have a situation here in which you're routinely working with data, which, if you look at it naively, looks completely independent. In other words, the amplitude of a sound wave from one point to another is independent. You know, it could go up as sharply as you want, could go down and whatnot. But if you demand something like this, if you put a bandwidth, if you say, well, the Fourier transform, I have reason to believe that the Fourier transform of that thing, whatever it represents, you know, it could be mass density, it could be a probability. I haven't said anything about that. You can naturally, you'll naturally get a constraint on that data, so that really there are fewer degrees of freedom than you think, and they're not, well, they're non-local. They're spread out, and they would lead to a violation of a form of statistical independence. Does that make sense so far? Yeah. Okay.
But if you think now for a minute, do you think there is any bandwidth constraint on your song?
If I think for a minute, give me a minute.
Not think. Think. If you give a song.
Oh, sing. Is that what you said? Oh, I thought you said think. Think for a minute. I was going to take the opportunity to rest. It's been a long day. No. Well, I mean, the limits in me producing a signal have to do with my instrument, right? Whether I can generate frequencies higher than 20,000 hertz, for instance. You know, why?
There will be frequencies higher than 20,000, even if you are not able really to give a pure 20,000. Just
harmonics.
Whatever. I believe that when you speak now, clearly there are frequencies which much more than 20,000 are there.
I'm not so sure, actually. I mean, I don't think if you did a spectrum analysis of my voice right now, you would see anything up there.
Yeah.
But I'm not sure why. Does that matter?
No, but then it seems to be an artificial constraint. And you believe that there is such a constraint for a theory. Is what I understand. But maybe I should let you continue.
Yeah, I'm almost done. But we can come back to this. I mean, this is not... what I did is I proposed a place that you might find a constraint. I mean, this is not... the place was the Compton wavelength. Okay? So if you had a natural scale in here, you can generate, using Planck's constant, you can generate a wavelength from a momentum. That was the idea. I mean, the audio thing is obviously, I think it was obvious anyway, is an analogy. But the general point about, I mean, there are many kinds of non-local constraints. The topological ones was another. Anything with a grandfather paradox, any time you have closed timeline curves, you're going to have consistency constraints, you know. So let me just say something about free will and why I don't think it's a problem. The data can never be completely freely chosen when you have a constraint present. That's what it means to have a constraint. That's true in electromagnetism. I can't specify the electric field in the region around a charge completely. I can't. It's not independent of the charge density. Okay. I do have some flexibility, but the divergence of the field at that point has to be equivalent to the charge density, or directly proportional. So there's always a reduction in the number of degrees of freedom. In the presence of a non-local constraint, the constraints come from data at other points. Okay. What does that have to do with free will? I don't think it applies a lack of free will, since our choices are not constrained so much as correlated with other spatially remote data. I also think, and the parenthetical here has to do with my
kind of, this is a general worry which sort of runs right through the free will determinism debate. If I'm living in a deterministic world, okay, even if I have no constraints and I have an infinite number of, not an infinite number of degrees of freedom, I just have the usual number of degrees of freedom. I can give a particle any position, put it anywhere, give it any velocity. In what sense am I free? I mean, I'm already confined, in a sense, by my past. Hume, I think, offered a nice compatibilist analysis of this. I'm not going to do a Hume exegesis right now. But I don't feel that there's any less free will in this case than there is in any ordinary deterministic theory. And I think it's a mistake, furthermore, to think about having my actions causally constrained by what's going on elsewhere. I think what you're looking at when you have non-local constraints, it's something like what you have with quantum entanglement. You have a kind of choreographed set of properties at distinct spatial points. So that's free will. Conclusion: in a relativistic theory with domains of dependence defined as I did by forward and backward light cones, I think it's useful to think of the failure of statistical independence, not so much, so many people here are thinking in terms of retrocausality, which is one way to think about it. I prefer to think about it in terms of non-local constraints at any given moment in time, that the data are correlated. Whether one could construct a theory with such constraints that reproduces quantum mechanics, and this is related to Lev's comment, is a challenge for your summer vacation, and it's only the beginning of July. So I'm really looking forward to seeing the archives, say the end of August, if anybody decides to take this up. I'll probably be done by mid-August, but I'm going to hold off on posting my results, because I don't want to, jeopardize the competition. And these are some references. This is most clearly spelled out, I think, the ideas here in this paper, non-locality without non-locality and foundations of physics, and online. And non-local constraints also come up in the work I did with Walter Craig on multiple time dimensions, in which you start with initial data on surfaces of codimension 1 that are, this is data for the wave equation. This is kind of empty if you don't talk about what equation you're trying to give initial data for. We showed well-posedness given a certain non-local constraint, which is defined on the momentum and frequency space. Related to this, I just wanted to say something about, there was, Dustin, is that right, the talk earlier about evolving sideways in time? And I don't know, the comment was that this may imply problems for presentism. I'm not sure whether that's the case or not. But it's you can do the same thing. So if you have as we did here, just in 3+1 dimensions, you can give data on a surface which is extended in time and 2 space dimensions and evolve it in the 3rd dimension. That result's been known for a long time, actually. It's in the back of a text, of a reference book that many of you have on your shelves. Surprised me. All we did is we figured out what the constraint was that made that evolution well posed, that made it stable under a certain norm. So that may be of some interest. But this is probably more, that paper is actually more directly relevant to this talk. Okay, that's it.